civil engineering. So Gabriel was a student of mathematical modeling. So he got his master thesis here in 2010. I was his supervisor, and then together we worked on his PhD, and then he defended in 2016. And so after that, he joined the global software company, and he works on more practical programs than before. So and today he will tell us about it.
I thought I can be. So thank you, Martin, for the kind introduction, and it's my honor and pleasure to be here in front of such an audience. As Martin said, I finished my PhD here 6 years ago. Then I joined the global company, which creates a software for civil engineering. It is an all-in-one software, to be honest. You can model things, so it has a built-in CAD. You can analyze with finite element methods, and you can also design your structures, which is pretty important for all the civil engineers. They do not like to overcomplicate things. They like to compute big structures. So it's not really easy to introduce some new concepts, some more advanced stuff, because they will always ask, okay, and what should we give as inputs? So this was the case also with our masonry. So something has changed here. Okay, so let me give a brief overview about the concepts. What do we as civil engineers consider under masonry? How can we tackle the mathematical modeling? What has been done already? Because as a disclaimer, I have to tell you that all the mathematics behind it is not really complicated or cutting-edge technology, what you haven't seen already. Here, the main part is the application, so that everyday civil engineers can get their input and they can compute their structures. So our part 3, the parameter identification or parameter fitting, will be kind of the novelty of the whole procedure, because this is what the engineers do really need. And I will show you some nice colorful pictures with some test results altogether. If we will have some time, I will go to my local computer at the work and maybe show you in action our software. How does it compute and how it's not. This was a joint project, actually, with Austrian participants. It was a 3-year project that we started in 2018, actually. And why it was really nice to be part of this project is that it did not come from theoretical people. Who initiated this problematics was the initiative at Siegel. They are all from the industry, and they needed some software that they could calculate masonry in a more refined way as before. Basically, no one had before very complex product or mathematical model that they could use also for larger structures. What I will be talking about, the mathematical models, they are actually implemented also in ANSYS, in Diana, and some other software, so it's not really very new. But we had the backup also from the producers of masonry, like Wienerberger. So it was I hope, successful project with many engineer gurus who also gave us their know-how, what they had experienced from real projects and what they were using. So masonry, what do we think of masonry? It has different parts. It consists of the masonry unit, which you can see here. These are what we call bricks. And as you can see, they have many different shapes. They can be of many different material. These are all clay material, but actually they can be of concrete, calcium silicate, also from natural stones, which are quite different. And one additional property which makes them quite unique are the holes. So usually they have, unless they are solid blocks, as here the first stone, and they are then categorized into different groupings relative to the whole ratio per volume, how much holes are in the unit themselves. And you can do some tests. These are photographs of actual masonry unit tests. You have some compression tests in both directions. So let's call here on your right picture the strong axis, because this is the better direction, what they usually want to load. And the perpendicular one is the weak axis because of the holes in it. This one fails much sooner than in the strong axis. So in a masonry, you have then the mortar, which is the binding material. This is usually limestone with some sand and cementitious material. Some notation here. Something open up. Sorry. We will talk about where do we bind the masonry units together. So in the horizontal direction, these are called bed joints, and perpendicular to them, these are the head joints. These can be filled or do not have to be filled. If they are not filled, you have the Eurocode standard, which says that then you need to have at least maximum 5 millimeters between the masonry units. And the special category of mortar, which they are not even mortar, are the so-called masonry glues. They are some polyurethane foams, basically, which bind together the units. Why they are so special? These are not really regulated by the Eurocode. They do allow for such binding units, but they have to be under some different technical allowances. So we also need to have a special case for these. I will talk about them. What I will not really mention today, we can have some concrete infill also in the masonry. So there are some different types of holes. There are some large holes in some masonry units. You can see here that here the hole ratio is very big. These are then the so-called grouping of a masonry unit. Basically the ratio of the holes to the whole volume. They are called group 1 up to 4. Group 1 are the solid blocks, and if you have holes in the masonry up to 20-25% of the volume, and here group 3 is I think up to 70% of the volume. These also have their own strengths, like compressive strength and shear strength of the concrete, which can be somehow incorporated in your final model. However, we do not regard them. They do increase a little bit the compressive strength of the whole masonry. but actually we are now on a more conservative side with such. And then you bind together these 2 or 3 things together, and you can make some tests. These are prescribed tests by the Eurocode. You have some flexural tests in different directions. You get some values, and on the right side, this is a standard compressive test to test the compressive strength of the masonry as a whole structure. You can get some Young's modules and different material properties, although not too much. What you would need for computation, this is very little, but we will get to that later. Here are some tests, some shear tests of the masonry. On the right side, this is without any compressive stress applied. This is called the initial shear strength, but you can also apply some confinement pressure and test the behavior of the masonry. And then this tangent alpha is basically some kind of a Coulomb friction coefficient in this case. And these are then all written into the papers of the masonry when an engineer gets a product values to their hands. So what we will consider, our assumptions are that we are dealing with 2D models. Like from masonry, you almost always build walls. So you do not need any 3D mathematical model. If you need to go that deep, you really need to apply different models for mortar, for masonry, the binding of these materials. In larger structures, you always want to model 2D. In our software, however, it's not like a purely plate model. We have a shell element. So our plane stress assumption is that only sigma z is 0, the transversal shear, which in mathematical language is the sigma 1, 3, and 2, 3 are non-zero. However, you can apply. I think every material model for masonry is a plane stress model. I haven't seen any other considerations, at least for practical reasons. As to the notation itself, we are dealing in our realistic 3D. So we always use the Voigt notation. My stress and strain tensors will be 3 or 5-dimensional vectors. Compliance matrix is also not a second order tensor, but a classic symmetric matrix. So I have just written Hooke's law for our isotropic material in its most basic form. This is what 80% of civil engineers use. They stop here. Also, my chef says that if you need to consider plasticity, he doesn't want to live in that building anymore. We will go a little bit beyond that, although, first of all, as you've seen before, like masonry is not really isotropic. So that is a very, very big assumption of what we have to get rid of. So we will for sure need orthotropic material, which means that we have orthogonal planes of symmetry, which masonry, of course, very nicely fulfills. This is already a step up from basic civil engineering. We do have a symmetric matrix. So although I have written here 2 Poisson radii, mu xy and mu yx, they are related to each other. So usually we define one as an input parameter and we get the other one. Also, just a notation, my gamma xy is 2 times epsilon 1, 2 in the mathematical notation. So that's for notation. We will need to go into plasticity theory, very, very basic assumptions. We do not need to go very, very deep. Some additive decomposition of my infinitesimal strains into an elastic and plastic part. We do need to consider multi-surface plasticity, so we can have different or more yield surfaces, which I denoted here, capital Fy. These can also change in time also, although I'm here referring to only some pseudo time because we are in rate independent evolution, so no inertial effects whatsoever. We imply our classical plastic flow rule with the plastic multipliers lambda I, although I can have also non-associated plasticity where the plastic potential does not need to be Fy. This can be some other GI values. Although I'm not really going into some assumptions here for some existence or uniqueness or anything like this. Let's assume these are well-behaved functions everywhere, although maybe not at the connections of my different surfaces. And we augment with the classical Karush-Tucker conditions for plastic flow. This is, I think, very, very standard stuff, so nothing new here or something that should be explained. I've written here the example for ductile materials like steel, the classical von Mises plasticity, where I have the same strength in compression and tension. This is called my small fyt, and fyc, y stands for yield. In the three-dimensional space, you imagine it as such. These are the principal axes, which I've labeled sigma 1, sigma 2, and sigma 3. This yield criterion, also called the maximal deviation, but actually it's related to the deviatory part of my stress. So hydrostatic stresses do not give rise to yielding. So this is what we work with. This is what we imagine. Although for masonry fracture in tension or masonry crushing in compression, we need strain softening. This is related to the following picture. So I have some inelastic work under the graph, and this is an exponential strain softening for my equivalent plastic strain, which drives hardening in this case softening. So the behavior of the yield surface. These are some notions from Zdeněk Bažant from 1983, where actually if I want to have mesh objectivity, I need to introduce another intrinsic length, which is here denoted h. This is sometimes called the crack width. So here my stress strain graph is actually not constant throughout my finite elements. this is mesh dependent, because if I want to dissipate the same energy, I need to adjust my stress strain diagram accordingly. Also, I have a second assumption here. This is an upper limit for my mesh size depending on my input parameters. This can yield to some so-called snapback effect, some non-realistic energy dissipation. So this is something what we need to take care about. But unfortunately, these are the drawbacks of these local strain softening models. More recently, there have been some non-local models as well. Maybe it would be like a good idea to take a look at those. But as I said, civil engineers are very conservative. So let's start with the simplest models we can have. So these are the tools we will use later. So let's get to masonry and what do we have from the literature. I think from the 1970s there have been different material models trying as much as possible describe the behavior of the realistic behavior of masonry. I think the main model is from Gans from 1985. I have listed some others, but these are actually some modifications of the original work from Gans. But as you can see here, they are not the most basic models. For example, this is the material model from Schlegel, from his dissertation work from 2004, which has 18 yield surfaces. So it includes also assumptions of the overlay between the bricks, so how far they are above each other, which then modifies some of my yield surfaces and some not. So if you recall my previous slide with the big structure, this is apparently not going to work. If you need to calculate big structures, I think to compute it with these models, it will take shorter time to build your structure and make the models. But as you can see, the basic assumptions are that you have very, very small tensile strength in both directions. So this is the weak axis. And we have some nice plastic surfaces for compression. Of course, this is why masonry is built. You always assume that they are compressed together. This is what holds the whole structure together. This is very similar to concrete, actually. There we also consider it without tension. So actually, what we ended up with is Paulo Lourenço's model from 1995, which is a composite Rankine Hill type yield surfaces. The nice thing about it is that it has only two surfaces, or actually the Rankine can be divided into two orthogonal surfaces, so two or three, depending on how you look at it. These are some iso shear lines, which you can see here, so you can imagine it in 3D in the Cartesian stress state. This is sigma x and sigma y are my classical directions depicted here. So we will tackle this model. This is actually what we ended up with implementing in our software with some additional assumptions. And as you will see, although this looks like an easy model, you still need 12 parameters to define these yield surfaces. And I already told that if we introduced only this model, nobody would use it. Like everybody would ask you, okay, and what should I input into these parameters? So we will go through over that as well. We made some nice engineering heuristics for the assumptions of these parameters. Okay, so the ranking surface, this drives my tension side. I have a yield surface with some little bit different notation, but my size are basically the stresses. These are shifted stresses by my so-called back stress. This comes from my hardening softening assumptions, which we will go through later. Why this is not the classical ranking yield surface is because of this additional parameter alpha. If I put alpha equal to 1, this is my classical ranking surface. Here we can modify it. Alpha is a ratio between the uniaxial strengths in x and y direction and tau u, what is the pure shear strength. In geotechnical analysis, you would call this cohesion, this value. So this accounts for the shear stress contribution to my overall yield surface. And we augment this with the softening rule because in tension we need fracture. This is this quasi-brittle fracture according to Bajan, this drag bandwidth theory, the exponential softening related to my sorry, I forgot to mention what is this h. This is my equivalent length of the finite element. So you take the square root of the area of the element. Quite easy. And we need the equation for the equivalent plastic strain rate, which is the principal plastic strain in a theory, which will equal to my plastic multiplier in case we assume non-associated plastic flow in this case. So we put here instead of alpha just 1. In that case, this reduces to kappa dot equals lambda dot and makes our life much easier. Very analogously, I have here the expression for the compression side for the yield surface, which is centered ellipsoid. It is basically a submodel of the more general Tsai-Wu yield criterion. Here again, I have 2 additional parameters, beta and gamma, which I need to define. Gamma again, like alpha in the ranking type yield criterion. This contributes or assumes the shear contribution to the overall surface. And basically what beta does is to rotate my ellipse around the shear axis. Here this weirdly looking strength is f 45 degrees is the strength what you would get from a biaxial compression test if you had the stresses equal to each other. So you compress with the same force in both directions or masonry. For compression, we have a hardening softening rule. This is a quadratic hardening, actually an isotropic hardening, because for both directions in X and Y, we have the same hardening, the same rate of hardening, followed by quadratic softening up to my kappa, my specular plastic strain, which we take half of my compressive strength, followed by an exponential softening, which models the crushing, the final ultimate state of my masonry structure. Again, from Bajan's Craig bandwidth theory, to fulfill mesh objectivity, I need to introduce this intermediate value where I change from quadratic to exponential softening to some fraction, again, including some fraction energies and the equivalent length. These are the assumptions. Whereas micron plastic strain rate is again reduced to the rate of the plastic multiplier if we consider work-like hardening. This expression is what we call the inelastic work per unit volume. In this scaled by the algebra or the mean value of my uniaxial strengths. So let's look at some comparison. What do we get and what do we lose if we consider this instead of other yield surfaces? The colleagues have done some comparison with blue lines. I'm not sure if you can see it very well from there. Inside is the Gauss yield surface with these 12 yield surfaces, and around it, so a little bit bigger with green lines. This is our Lorentz-Foss model, the ranking hill. As you can see, I think these data points are from actual test data published by Ganz and Türlemann. So, of course, Ganz's model fits really nice with his own experiments. Anyway, you can see that we are a bit on the non-safe side if we consider failing at a higher compressive stress than in reality. So this is something we need to keep in our minds. Usually we want to be on the safe side. So if we don't know some parameters, we want to be on the safe side. So take a little bit less what we can consider. What is a nice thing about this ranking hill surface, although it's a multi-surface plastic model, that means that where they meet these two surfaces, they are non-smooth. Also, the ranking yield surface itself for zero shear. So here, Mike side 3 is 0. This has an apex. However, we can regularize this surface for nice computation. We can get much better results. This is also not really new. This is published work already. What you basically do is add some regularizing term, this mu square, which renders my non-smooth surface into a hyperbole. And in turn, we can use so-called super quadrics, which in this case is a super hyperbola. So I do not take second exponent, but I change it to the power of n, and the whole is then to the power of 2 over n. And you can see here, I did not change the apex, so this is the same. Although it looks like straight lines, this is not. So this is surface for n equals 32, very regularized one. So you have some high curvatures around these edges, but this is still smooth. My compromise, what I didn't make is this distance. This is mu times square root of 2. So actually, in this 2 mu by 2 mu square, I'm not really following my initial hypothesis that for uniaxial loading, I get uniaxial response, because here my return mapping will give plastic strains in the other direction as well. So how can we amend this? The procedure is that you shift your backstress by a little bit larger value than this square, this 2 mu by 2 mu. So in the literature, I found they shifted by 2.5 mu. So you are outside of the box, and you introduce some small tolerance. They say 10% of the minimal strength is fine. So in the area where you had the non-smooth contact, the apex, now you have the same behavior, like qualitative behavior, shifted a little bit, but you still get a smooth surface. So the question is like, how big should I get my n and n factors? Because if I have it very high, then again, you have some problems with convergence, because you have very high curvatures around these points. This is heuristics, I think, for n here. What I have, they suggest 12 or 24, and for wait, sorry, I'm a little bit ahead of myself. So for this n, 32 or 24 should be okay. And we can now sample our two surfaces into one. In general, how these super quadrics work, if you have more surfaces described by Fy is less or equal to 1, you make a sum of these with a power of n. So this is the regularization by super quadrics. This was first introduced by Alan Barr, actually in 1981 for computer graphics, somehow to smooth out surfaces. So for my super hyperbolic Rankine surface with the power n, I make it into a fraction so that I get this kind of expression with the numerator, the expression what we had before, and then the denominator, so that I can get on the right hand side this number 1. Very, very analogously, actually for the Hill criterion, I already have the number 1 there because it was an ellipsoid. I get the same expression or a very analogous expression to that one. And if you combine them into one equation, so this is my second m what I was first talking about, you get a smooth surface with one equation, and you do not have to go into some subdifferentials and dealing with some non-smooth yield surfaces, although maybe that would be also a nice addition to the model. You can see here some contour lines of my final yield surface, and this is again iso-shear lines. So this is into my third direction. How does it look like? So this is the nice thing about the Rankin Hill surface. Although it's quite complicated, you can make it into a simple singular surface plasticity model where you have your favorite apparatus to deal with some classic elastic predictor plastic correction, some radial return mappings, and all this stuff. So okay, so we have seen that we have many parameters that define our yield surface. Actually, already Paulo Lorenzo proposed some test experiments with which you can define at least the strength parameters. These alpha, beta, gamma. Guess what? In practice, you have this experiment. So no one else does any of these other experiments. What I know of, I think Wienerberger does this compression test. None of the other producers of masonry do. So again, if introduced just this model, it wouldn't really be helpful for engineers or for producers. Like to conduct all these tests, it's very laborious and quite expensive. So nobody will want to go into these tests unless some standards prescribe them. They do what is the minimum, what they need to do, and that's what you have to work with. So we need some better guesses in this case. I have to say. So let's tackle them one by one. We have 4 elastic parameters to define my elastic region in the orthotropic regime. We have 7 strength parameters, the different uniaxial, compressive, and tensile strengths, and these alpha, beta, gamma to shift around my yield surface, and these additional inelastic parameters. Kappa P, I think I haven't really talked about much. This is the equivalent plastic strain at peak compressive stress. So where my hardening ends and goes into the crushing state. So let's start with the strength parameters, because some of these are quite straightforward and they are well defined also by the standards. Here we are talking about the Eurocode, especially Eurocode 6, which prescribes the foundations or what should be considered for masonry in Europe. Actually, for our classic mortar masonry, we have some tabulated values. The compressive strength in the strong axis, which is in our notation the y direction, is computed from 3 values. This is k times the compressive strength of the masonry unit to the power of alpha times the compressive strength of my mortar to the power of beta. One little note, maybe you have also noticed, so if fun fact, if you make some unit checks, this will not work if your alpha plus beta is not added up to 1. So I needed to check this with the guys who deal with the Eurocode day by day, like how to actually assess these things, because in our software internally we always have SI units. So how should we relate to these? For example, you can see that thin layer mortar does not even consider the mortar strength. It's so thin that you just omit it from your compressive final compressive strength. So you have like Newton per square millimeter to 0.1 to the power of 0.1 unit. So you need to take care, or rather not, leave it to the civil engineers to deal with such stuff. Of course, we have some exceptions. I'm not really sure how these are called in English. Internally, we call these old style masonry. These are my, sorry. Yes. So these are the solid blocks, what everybody has seen and used. These are not really used anymore. This is why we call these old style masonry. Nowadays, you have one block per wall thickness. However, here you have some layers with two masonry units, and above that perpendicularly you put one unit. However, this structure then reduces your overall compressive strength. So here the Eurocode says prescribes a 20% reduction in your overall compressive strength. And again, if you consider blued masonry, this is completely different story. We need it as an input parameter, but usually these tests are conducted, so we do not need to go into some tabulated values. Fun fact, usually you have on the product sheets also the compressive strength for the masonry, but you have to use the Eurocode. Like the Eurocode in civil engineering is basically your Bible. So if you have a better model, you have to adjust it to comply with Eurocode, because that is what every civil engineer will ask you, and does it fulfill the Eurocode or not? So that's why we also, although in our database we have these compressive strengths, we recalculate them according to exactly this formula. Okay, so what about the other direction? So our weak axis. Here we are getting into some shallow waters. Like the Eurocode doesn't really deal with that. You do not have much data at hand. So what our colleagues did at the Graz Technical University, they looked at some recommendations from the German codes. However, this is my pink line. This was very conservative, so they rescaled that to another line and made it into a much easier expression. I'm not sure this was necessary. However, this gives a nice assumption. Again, as this is my weak axis, I can have filled or unfilled head joints, which then reduces my overall strength. If it's unfilled, of course, the mortar has no additional effect on my overall stress. So you, in these cases, in the X direction, you almost always have some reduction factors. Here it's to 35% of my initial compressive stress. Okay, so we have the compressive strength. What about the tensile strength? This is again, let's call it an engineering way to compute things. How to assess it, or how to explain it very briefly. You have some tests, or actually also the standard. I will get to the picture in the following slide. However, I need the graph here as well. It prescribes the shear failure under some confining compressive stress. This is this basically called friction. style graph with the initial shear strength FBK. So what my colleague did is to assume I have 0 Poisson ratio. So I have my confining stress in the respective planes. So in the normal stress versus the shear. He extrapolated it into a linear plane, and he was asking where is the center of a sphere that emits this plane as the tangent to that point. And in that case, I hesitant to call it Mohr circle, but it's kind of like a Mohr circle approach. In that case, where that sphere touches my normal stresses, I define my respective strengths in the uniaxial direction. Again, with the weak axis, you have some reduction factors if you have filled head joints or not. These are all taken care of. So Ux in the weak direction is half of the friction angle in the strong direction, and you consider it 0 if you have unfilled head joints. However, in that case, the initial shear strength is also reduced to half. So that's it. What remains from my strength parameters are the alpha, beta, gamma for the Rankine Hill surface. These are, I think, the most exotic ones, so nobody will know how to compute. Maybe even these they can fill in. Beta is the easiest one. So already, although Lorenzo said that we do not need to make any adjustment to the rotation of my ellipsoid if we are considering different masonry. So this is taken always minus 1.05. We've had good results, he had good results, so we believe him. This is what we work with. Actually, this is the easiest parameter. And what about alpha and gamma? So these are a little bit more problematic. Again, I have to put here a graph. Here we at least have some guidelines from the Eurocode. This is my shear strength relative to the confining compressive stress to the wall. So if you have small compressive stress to your wall, then if you apply shear to the wall, it will first fail in the bed joints due to friction. If you have moderate confining compressive stress, then your masonry unit will fail under tension. This is my second part here. And lastly, if you apply too much compressive stress, then usually you just crush your masonry. And this crushing quite abrupt part. So for a typical case, this is how it looks like. This part is described also in Eurocode 6. So we have the guidelines. The crushing under very high compressive stress, this was described by Mann and Müller already in the 1970s. So these are well-known theories. So what we assume here, we can compute sigma 1 and sigma 2, where these lines cross each other, and we compute the mid value. And this is a middle shear strength, a little bit modified with a factor 1.1. So we do not take it on the line. And let's say that we want to have our Rankine and Hill yield surface cross exactly at this point, sigma m and tau m. Actually, I have a little mistake here in my graph. The Rankine surface should go through my initial shear stress strength here, this is 0. sorry for that. Imagine this is going this way. And actually, from these assumptions, you can already calculate alpha and gamma. You have 2 points on your curve that defines it. We have some special cases. What about the crushing happens much quicker? In this case, you do not get onto this plateau, but even before this shear stress, you have crushing of your masonry. In that case, we define our additional point exactly at the crossing. So my two yield surfaces should look like this. Again, my green line should cross this point as well. And we have a very nice, quite easy expression for alpha gamma. Each value is known. We before computed the tensile strengths, the compressive strengths, and then I just need to compute according to these two cases the middle point of sigma and tau m. Okay, we have all our strength parameters. We can go to our elastic moduli. Epsilon y, this is my strong axis. This is again something that is prescribed in the Eurocode. This is 1000 times my compressive strength, which we modified with a little factor. Actually, with this modification, we are ahead of the Eurocode. So the guys who suggested this, they were suggested also to the Eurocode committee in their next version. So it's a nice addition to work with such experts that have these insights. This modification factor is tells you how many bed joints are there per unit height of the wall. Because if you have short masonry units, then you have many bed joints, and this then, of course, reduces my elasticity modulus. In the weak axis, again, we have some reduction factors depending on whether we have filled head joints or unfilled head joints. This works again with the compressive strength in the weak axis very similarly. Poisson ratio is set to 0.2 or 0.1 depending on the grouping. Let me remind this: grouping means how much holes or how much void is in my masonry. So if it's a solid block or very small holes, I take 0.2. If there are too many, then 0.1. This is not described in the Eurocode. This comes from experts, what they usually do, and they are satisfied with their own equations. It's something which you will not find like this in any literature. And the shear modulus, again, taken from Eurocode, this allows for 40% of my elastic modulus in a strong axis. I put it here that we are dealing with plate models, so we have transversal shear. We need some shear moduli for them as well. Of course, if you don't have experimental data, you put it equal to the one that you know. So this is what we do. We make them equal to 0.4 times EY. And that's all I have to say for the elastic properties. What we need to do are the inelastic properties, the parameters, where we kind of go into the most of the guessing game. So we have some fracture energies, both compressive and tensile in both directions, and we have the peak or the equivalent plastic strain at peak compressive stress. At least for tensile fracture energies, we can take some test data from concrete experiments. So what you can see here, these are not done on any masonry because there are no crushing or fracture test data for masonry available, unfortunately, at least to my knowledge. So at least van der Ploem has a publication where he related the tensile strength to the fracture energy. Sorry, I don't have my axis labeled, but this is the tensile strength and this is the fracture energy. So we put a very easy expression that fits this curve. I think we will not be really that far away. If you think about like clay, at least in itself is very similar. These experiments were done on concrete with maximum aggregate size of 8 millimeters, so very fine concrete. I think that qualitatively, at least, we can be very close. Where I think this will fail quite badly are natural stones. So they are very brittle. I don't think this one will fit. We will see. Fortunately, 98% of civil engineers will use clay blocks belonging to category group 1, 2, or 3, and that's why maybe some concrete blocks where this can be immediately applied. As to the equivalent plastic strain, again, we do not have very much data at hand. So we use a table from EC6, which points out two points on your stress strain diagram that should be included depending on your grouping of the masonry. Epsilon M1, we assume it will be our strain at peak compression. From where you compute the equivalent plastic strain, you just take away the elastic part. And the second point is epsilon mu, so it's not really visible. This we will consider the turning point in your crushing diagram from the quadratic softening into the exponential softening. That will define our second point. Let me go here. This is the equation for compressive fracture energies. Again, no test data are available. No literature is found. So what do you take? We want to be on the conservative side. So we take the least admissible fracture energy that Paulo Lorenzo's model admits. So this is the smallest energy that is still physically viable. If it's not really, sorry, okay. It might not be very realistic, but at least we are on the safe side. So unfortunately, right now, this is the best we can do. We have also defined our equivalent length, what meets this crack width, taken from some test data, how actually these compression tests are conducted in real life. And now we have defined all our parameters. This is a comparison of our model, which is the green surface, with the original model from Lorenzo. And you can see that for some test data, we are actually better than the original Lorenzo's model, which is quite nice. Maybe you have noticed that these or test data are around the perimeter of all my yield surfaces, so nothing like that would define. This would mean, if you remember, these are my normal stress axes, and in the direction is the shear. So that would mean you would need to apply very high shear, so that you would need some test data from some earthquakes, basically. So that's why all the test data are around the perimeter. What happens inside in the top, nobody really wants to know, I guess. These are some other test data. I wanted to show also that not everything is very happy. Some test data are quite off from our model, but at least we can again say that we are on the safe side. So all the test data that they say where failure occurs is above our stress or yield surface. So let's see some nice colorful pictures for the end. This is a real shear wall experiment where you have your 3.6 meters long wall. You apply some confining pressure, and this is actually a strain-driven experiment, so you do not push it, but you pull with some mechanics. And this is how it looks actually already in our software. This is the confining pressure that you apply as a surface load. So you redistribute it onto this top part is actually concrete. We consider it linear elastic. Nothing special happens there. And you apply some different deformations to the top. So this is where you are pulling or pushing, depends on where you look at it. These are what we call the non-linearity ratio. These are the elements that are already yielding. And you have some nice non-linear curves. This is where the failure happens. So this is in tension, and this is already in the compression zone for the masonry. And if you compare it with some real test data, this is my blue line, you can see that we've tried different input parameters, so we are quite close to what is really happening. What this blue line is, what you would do as a civil engineer as a hand calculation. So this is where you would put your yielding. This is where you would stop and say that you need to refine your structure because it's overloaded. And some different test scenarios again. We are on the safe side. This is basically what these tests are telling. If we are close or not to the actual data, hard to say. So far, this is the best we can do. This is a third wall, very similar. What is changing is the confining pressure. And very similar example, you take a variable wall width, you keep constant your confining pressure, and you are looking at the shear stress or the shear strength of your wall. So a 1 meter wall, we get very good results. 3 meter wall width, also very good. Where it gets kind of iffy if you have a wider wall. This is already a little bit different. And I think that's all. This is all